Welcome to our 10th discussion. In today's discussion, we'll focus on sections 2.7 and 2.8 on the definition of a derivative. In this video, we will do an example involving the derivative of f of x equals x squared. So first, I want to recall that there are two forms for the definition of the derivative. For the definition of the derivative. Okay, and I want to draw a picture to illustrate both of them. So I'm going to draw some axes. I'm going to draw some axes here as well. And then I'm going to draw a graph. So let me just make my graph kind of curve upwards like this. And then I'll draw the same general shape. Okay. And in this first graph, I'm going to label this x coordinate. I'm going to call this x, and I'm going to label the point on the graph there. So if this is y equals f of x, and same thing here, I'm going to say this is y equals f of x, then at that point, I can label it, its coordinates are going to be x comma f of x. And then what I want to do is, I want to be able to find the slope of the tangent line to this curve at that point. And our method for that is we pick a point that's kind of close to it. I'm going to call this x coordinate x plus h, where h is going to get really small, really close to 0. So if I draw the dot at that point is its coordinates are x plus h comma f of x plus h. So our idea, if we remember from before, is to connect these points with a straight line that is a secant line. So this is a secant line. And then we're going to move the point that has the x coordinate, x plus h, closer and closer and closer to the point where the x coordinate is just x. In other words, we're going to let h get really, really close to 0. And as we do that, our secant line in this picture will sort of flatten out a little bit. And now I'm going to draw the tangent. So the tangent will look something like this. It matches how steep the graph is right at that point. So this is our tangent. Okay, so we call the slope of that tangent line the derivative. And we write f prime of x to indicate the derivative. And the slope of that tangent line involves finding the slope of the secant line first. If I find the slope of the secant line, it's f of x plus h minus f of x. I subtract the y values. And then over, now I subtract the x values. X plus h minus x. And then we're going to take the limit as h approaches 0, and that's what makes it the slope of the tangent line. All right, so this is going to represent the slope of the tangent line at x. And I can simplify this because the h's cancel. Sorry, the x's cancel on the bottom. And that leaves me with the limit as h approaches 0 of f of x plus h minus f of x all over h. So our derivative is equal to this. This is one of the forms for the limit definition of the derivative. The other form is really similar. So in the other form, we say, okay, I'm going to call this first kind of reference point. I'm going to call that a. And so its coordinates are going to be a comma f of a. And the other point, we're going to call that x coordinate, just x. So we can label that point as x comma f of x. So if we connect these with a secant line, that secant line will look something like this. So we have our secant. And now if I draw my tangent line at a, that'll look something like that. Because as I move that point at x comma f of x closer and closer and closer to the point with x coordinate a, that secant line in this picture gets a little flatter. All right, so in this picture, if we write our derivative, this would be our derivative at a. And first I'm going to write the slope of the secant line. So change in y on top, which is f of x minus f of a, over change in x on the bottom, which is x minus a. But to make it the slope of the tangent line, I need to take a limit. I'm going to take the limit as x approaches a. All right, and that is another form for the definition of the derivative. So next, let's look at an example where we use these definitions of a derivative. But first, let me say that this second form represents the slope of the tangent line at A, when the x-coordinate is A. All right, so to this example. So we're going to look at, this is a problem from worksheet 5, and we are going to look at problem number 2 first, and then we'll look at part 1a. So we have the function f of x equals x squared, and I want to find the derivative using the definition of the derivative. So let's do this using both definitions. So we'll do this, I'll call my first way method 1. Let's take the limit as h approaches 0. Let's use that definition. Okay. So first, I'm going to give you 3 minutes to try this on your own. 3, 2, 1, pause it, and try this one for 3 minutes on your own. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about 3 minutes. So our derivative f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. So if we evaluate this now, we have the limit as h approaches 0. When I plug x plus h into my function for the x, we'll get x plus h squared. And then f of x, we know is x squared. So we have that all over the h. Okay, so we have limit as h approaches 0. Now I can expand x plus h squared to get x squared plus 2xh plus h squared, and then I get minus x squared all over the h. Okay, so now I see the x squareds are going to cancel, and that's nice. And on the numerator, both of the terms now have an h remaining. So let's factor that h out, and that'll leave us with 2x plus h over h. And now the h's cancel. And after they cancel, now I can plug in. So I can plug in, and I'll get 2x plus 0, which is just 2x. Okay, so we've gotten our derivative. Thus, our derivative, f prime of x, equals 2x. So let's now do it using our other limit definition, just to show that we get the same thing and to compare the two methods. So the second method is we're going to do the limit as x approaches a. And I want to first give you a chance to try it. So pause that video for 3 minutes. 4, 3, 2, 1. Pause it and try it for 3 minutes. Alrighty. So hopefully you did that. Hopefully you paused it and tried it for about 3 minutes. Let's talk about it together. So this definition of the derivative says f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. So we get the limit as x approaches a. F of x we know is x squared, and f of a, if I plug a in, I'll get a squared, and then over x minus a. Okay, so I'm running out of room at the bottom here a little bit, so let's go to the side. So we have this limit as x approaches a, and now I see that the top factors, it factors as x minus a times x plus a, and then over x minus a. So we get some cancellation. These x minus a's, they cancel. And now we are good to plug in. So for that x, I get to plug in a, which gives me a plus a, which is 2a. And that's good because it looks like the 2x. It's just we have now taken the derivative at a. So it makes sense that we are getting 2a rather than 2x here. So when we do a problem using this x approaches a definition, we have to remember what the original variable was, which was x. So if that's the case, we are going to, at the end, switch to that original variable. So we're just going to change those a's to x's. And if we do that, we'll get f. So we had f prime of a equals 2a, and if we switch it, we'll get f prime of x equals 2x, and that is our derivative. So if we do a real quick comparison of these two methods, they both give us the same thing. In different situations, one of the methods may be slightly shorter than the other one. Like in this problem, I would say method 2 is a little bit shorter. That won't always be the case. In general, the h approaches 0 method typically will involve more expanding, like we saw in this step, but the factorization that happens is typically easier. With x, oh, and because of the expanding, it has more terms, like there were more terms in this numerator. But as x goes to a in that form, there is typically more factoring, like we had to do difference of squares for this factorization, but there end up being less terms. So those are some of the key differences. All right, so I want to now ask the question, does this derivative, does this make sense based on the graph? Okay, so our function f of x equals x squared, and if we draw the graph of that, this is a parabola, an upward facing parabola that has the vertex at the origin, so it looks something like this. Okay, and now I'm also going to graph the derivative. So my derivative f prime of x equals 2x. So if we draw the graph of that, I'm going to draw some axes, and 2x is a line that has a slope 2, and the y-intercept is 0. So that line is going to look something like this, going through the origin, but the slope is 2. All right, and now I want to make a table of values and just look at some points to see if the derivative kind of makes sense based off of the original function. So I'll keep track of x, and then the derivative. So if for the x, if I plug in 0, that's talking about this point down here. And at that point at the bottom, if I draw the tangent line, the graph is sort of perfectly flat at that point. So my tangent line is going to be horizontal. Okay, so that is the tangent line at x equals 0. And notice that the slope of that is 0. So if I go to the derivative graph, and I draw the point where x is 0, notice at this point the y value is 0. And in general, that's what the y values, or the outputs of the derivative, tell us. The y values of the derivative, these are the outputs of the derivative, and they are supposed to represent the slope of the tangent lines to f. So the fact that at this point the y value is 0 is telling me that in the original function, the slope of the tangent line should be 0. And it is, if I look at it visually. Okay, and I forgot to mention that when we plug 0 into our derivative function, we get 2 times 0, which is 0. All right, let's plug in some other values. Let's plug in x equals 1. If I plug that into the derivative, 2 times 1 is 2. So now, when x equals 1, I'm going to draw the tangent line. And this tangent line will look something like this. So it definitely makes sense that the slope of that should be positive, so a number like 2 seems reasonable. And if I go to my derivative graph, when x is 1, and I plug that in, the y value is 2. So the y value is the output of the derivative. That's telling me that if x is 1, the slope of the tangent line to the original graph should be 2. And that makes sense based off of our picture. All right, let's also plug in x is negative 1. If I plug that in, I get 2 times negative 1, which is negative 2. So if we draw the tangent line when x is negative 1, somewhere over here, and draw the point on the graph, and now let's draw a tangent line, something like that. It's got to match how steep the graph is at that point. That definitely seems like a negative slope is good, so something like negative 2 for the derivative makes sense. And in the derivative graph, if I go to where x is negative 1, and I plug negative 1 into this, I know I get negative 2 out, so the y value is negative 2. And that's good. The y value of my derivative function is the output. That's supposed to tell me the slope of the tangent line in the original graph. And it makes sense that that could be negative 2. All right, let's end this video with a specific tangent line example. Let's find the equation of the tangent line to f of x equals x squared at the point negative 2 comma 4. I want to first have you try this for 3 minutes on your own. So 4, 3, 2, 1, pause it and try this for 3 minutes. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for 3 minutes. Let's talk about it together. To get the equation of any line, we need a point. We need a point, and we need a slope. Okay, and a point is easier here because we're given it. The point is just -2, 4. For the slope, the thing that tells me the slope of the tangent line is my derivative. So we need the derivative. And my point's x coordinate is -2. So I'm going to have to plug -2 into my derivative. All right, so we know what the derivative is. We know f prime of x equals 2x. So let's plug in -2 into that. So this implies that f prime of -2 will be 2 times -2, which is equal to -4. So that is going to be the slope. So the slope is going to be -4, and the point is -2, 4. All right, so we are now ready to write down the equation in point slope form. We'll get y minus the y coordinate of the point, which is 4, equals the slope, -4 times x minus the x coordinate, so minus -2. So double negative becomes a positive. I can simplify this and get y minus 4 equals -4 times x plus 2, and that's my equation. It's totally fine to leave that in this point slope form. But if I did want to put it in y equals mx plus b form, I would just distribute the -4 first and then isolate y. So I'd get y minus 4 equals -4x minus 8. And adding 4, we get y equals -4x. Whoops, not plus. We get -4. And that would also be a fine way to leave my equation of my line.